this time we will exactly solve a similar counter, a modulo, well, just an arbitrary large number. For example, 1572 different states, a counter like this, a counter modulo 1572. And we will solve that, this large number of states, because we will change the plan. This time the plan Y. And this is because we will not go and enumerate all the different states. There are too many. So you see, we will use arithmetic operators like current state is current state plus 1, this way. That easy. So from this perspective, you see, we have the same circuit as usual, which is in this case a simple counter with a typical terminal count, the binary code, 11 bits of the binary code, the count enable, the clear direct, and the clock. This time, for example, in order to show you that it works the same in one way or another, we can use active low signals for everything. So you see, for the first time, you see everything is sensitive to the falling edge, because in some way the microprocessor allows you to configure the edge that will generate interrupt, whatever it is, the rising edge or it may be the falling edge. It doesn't matter very much. You can do that because it's configurable by means a bit in the init system. That is what is going to happen here. And then the function table is as usual. It will go up using this modulo counting, and then you can very well organize a timing diagram as usual, right? For example, terminal count is 0 all the time for all the 1571 states, because in the 1572 state, you see the last one, you have a pulse. So that is a kind of a frequency divider in some way by this number. All right. So this is what we have in mind. The same way as before, we will talk about the hardware, the software, and we will go developing and simulating at the same time, generating the schematic in Proteus and the source file compiled using the MPLAB-X and the compiler XC8. And we will do that again. And again, it means the same kind of questions has to be answered, but this time this counter. But, the same kind of questions and strategies and final measurements, and naturally in the end you can go and modify this teeny example to convert this counter into anything else you like. Alright, for example, this one is easy transformed into something like a universal counter, where you have, the load, if you like, to input some data in, so you can jump from any state to any other one, and then you can make that thing reversible again, up and down, in that way, so no problem, right? But now let's go and follow again this line of reasoning to try to solve the many bullets, because this is what is of interest in this example tutorial. Okay, so there is the other example on counters and finite state machine that you can design, okay? This idea of using external interrupts and a specific way to organize the software to implement finite state machines. So you can jump to P10, and in P10 you know that there is this 4-bit serial transmitter, and then there is the learning material and theory, and here you have what we are talking about. This is the first example that you've been developed and recorded previously, and this is the other counter. The first one was just a kind of a circuit that has only 10 states, so you can, if you like, enumerate them as in any other finite state machine, but this time you have a lot of states, so you have to take another strategy, like the plan Y, okay? Let's imagine that, the current state, for example, is a variable type int that has enough capacity to hold that large number of states. okay? And if, for example, the variable is type in, you can save this way as every state as a different binary number, for example. And if it is a 16-bit wide, okay, if this is what you've got, a variable that is 16-bit wide, you know that you can save 65,536 different states with 16-bit int variable. So that is what we are proposing you, right? To go and try to solve this counter, but you know, the recording is going to go a lot faster because everything else is the same, except that now you are planning a large counter and you have to change, you know, this strategy in a way that you are saving the current state variable. So here it is the difference. So let's go down the counter example, and as usual here you have everything, okay? So you can browse very well all this web page, you can zoom every single image, and in the end you have it all here to study, okay? Everything. So it's up to you now and repeat this kind of analysis and this kind of study time so that you can grasp all the main ideas, okay? The specification section is not that complicated, okay? The only thing now is that we will use perhaps active law just to show you that you can program that as you like, okay? And the function table is as usual. This time you are going to count in binary, but up to this modulo, right? And this modulo means that the last state, okay, is that number. That number is exactly 1571, okay? So when this number is detected, you will impose that going back to 0 that way, okay? And this is going to happen if you let the system go counting, because if you stop counting or you prevent the system go advancing because the count enable is not in the right level, read in the right level, well, the count will be kept. So that is what you have now in your hand. So very well, the same state diagram or a similar one, and so on and so forth. You can plan the state diagram in the usual way. Okay, remember that that is a good thing to remember. Please remember that when we talk about Q, this is bar Q, okay? And if 0 and this number, so be careful because it's bar Q, and you know it's a kind of an int variable, 16-bit. So you can now, you see, even if you have not gone through the picture, you can represent very well this variable. It's going to be like this, 16 bits now. So you have to generate the 8 most significant bits, and then the remaining 8 least significant bits, and this is the bit 0, and this is the bit 15. So you have, you see, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, and 11, right? So this is the Q10. So this is where this variable is going to be held in memory. So the other remaining 5 bits are going to be zeroed that way. Simple, right? So that's the tactical thing. Another variable is, as usual, count enable is the same bar. Count enable, and because it's a single bit, you will do the same thing. Bar count enable like this, 8 bits, and you will zero all the leading bits except that one that is of your interest, the bit 0, right? This is where you are going to save the value of this pin once it is read. Okay, so that way. So let's go advancing this time faster and faster because there is nothing else to explain about these differences on the variable size. Okay, so you can go browsing. The hardware is exactly the same. Be careful because the clock is devoted to one of these external interrupts. The point now perhaps is that you have 11 wires in several ports to be designed as outputs, and the same thing, okay? A different project name, counter modulo 1572. So once you've got the hardware in a sketch, you go the same way, the same pictures for the software definition, the structure of the hardware and software diagram. You know, remember what is happening here. You have a falling edge from this signal. You have an external circuitry that detects the edges. So in the end, you have a flip-flop that is set to 1 because you have a falling edge. Okay, this time, exactly this time when this happened, this hardware flag goes high. And if you have allowed this kind of interrupts, this one here means that this one can go through the end. And if you have allowed the general interrupts, this one is going to generate the interrupt vector. So the program will be able to go out of the main loop to somewhere else, and this somewhere else is nothing but the interrupt service routine, and it will be able to come back to the next instruction in the main loop. But what is going to happen in this jump, you know very well now, is that the bar clock flag is going to be set high, and the int, this memory position, that one, you see this register, this internal register, the external interrupt 0 interrupt flag is set to 0 that way. Okay, so that later on another flag can be detected in the same way. So when you do that, this int external flag comes back to 0, and so you have no other access to the interrupt service routine until this event happens again later on in time. So that is remarkable, and that is the great thing in this kind of a structure and architecture of a microcontroller, because naturally when the things start being complicated or with a lot more features, you have many sources of interrupt. Okay, that is the thing. So you have a main loop running, a kind of an operating system running here, and you can be interrupted because several reasons. That is what is the point, okay? So very well. And then the variables, you see the picture of the variables is different because you have the current state and the bar Q different this time. All right. Remember that in this plan Y, perhaps this is something that I have to write here again. In this plan Y, remember, we simply do that thing that is here, is looking like this. Bar Q, this is the CC2 job. You see, bar Q is just a photocopy, if you like to call that way, of current state. That way. A photocopy. So this CC2 is a lot simpler now, because internally you already have what you want to be in the LIDI section. All right. So the configuration of the many port pins, the flowcharts for reading and the flowcharts for writing as in P9. So just go back to P9 examples and recording and establish this, because you know that is necessary. And then you see the same picture for the interrupt service routine, these ideas that we have commented already. And finally the state logic, you see, going from one state to the next. But this time you see there is no case. You cannot have a case or a switch case of 1572 levels. That is impossible. Okay, what is possible now and a lot simpler is doing that kind of thing. A general if associated to the clock detection. Is that right that you have this flag set high? Yes, if this happens now you may do something or not, depending on the bar count enable. If this count enable is set low, the level, you see, you go back without doing anything. So that's simple. So that is a lot. If you follow this way, the main loop is a lot faster than if you really have to change the stage, because if you have detected, you see, if you have detected the clock falling edge and this is set high, you follow this way, and this way has a lot more instructions than this way. You see why the main loop is reading the inputs at different times, cyclically, yes, but not all the time at the same time, because sometimes the code is faster, or even this way is faster, and sometimes the code is longer. And why is longer? Because you have an idea in mind. You see, if this is happening and this is happening, and the current state is not the last one, what you like to do is this basic arithmetic instruction. Exactly with the same way that we did that in BHDL. Okay, remember? In BHDL, we add 1. We said something like current state in BHDL, right? Current state equal to current state. Oh, no, in BHDL it was different. In BHDL it was what? In BHDL it was different, remember? You have the current state and the next state. So in VXDL we said something like this: next state, the output from the CC1 is equal to current state plus 1, and this plus is the arithmetic operator that was understood correctly, because you loaded there, you remember, the arithmetic library, okay, the IEEE arithmetic standard library. So this symbol was understood as an internal adder, a binary adder of 11 bits. So now it's pretty much the same, but you don't have to worry about if the others or anything else, because the arithmetic is solved in the CPU arithmetic and logic unit. You see, the CPU has a very powerful arithmetic and logic unit of 8 bits. So now if it has to save a 16-bit operation, it's going to be solved by means of several assembler instructions. But this is the instruction, and this is very easy to write in C, okay? Naturally, it has no problem to write that in C. You see, current state plus plus semicolon, or current state equal to current state plus 1. That's it. But in the case that's the last state, if this is the 1571 state, the next state is the 0, not the next one. So this is why you have to compare. This is another arithmetic operator. You see, it's a comparison here. What you've got, a comparator. So if you have this comparison setting a yes, you simply go to 0. That's the way you have to count that specific number of states, truncating this 16-bit integer variable to be 11-bit size of 11-bit, but just not all of them high, but just the number 0 hex. This is hexadecimal 623. This is the number in binary 1571, right? So that's the way to go. Naturally, that you have to do the same with output logic. That has even a simpler diagram, you see. This is the photocopy. Let me remark you that, because it's important, right? Simpler, a photocopy of the internal state, and then the logic associated as usual to the bar terminal count. Okay, guys? So you can go continue just to the section that is related to the development and testing that you will do at the same time, because you have the advantage of the circuit already captured in Proteus and the software already implemented in the file. So now is your turn to go to the virtual environment and solve that for real. Okay, so let's do that. Okay, so let's develop that circuit. So this is the hardware. Save the link as in the right place. Computer, CSD, and now P10. And now we have to generate a new folder with the right name. So new folder, and that's the right name, counter modulo 1572. This is the place where to save this hardware and the software. Save the link as in the same place. So now you are with the two files of interest, the hardware and the software. So now it's your turn to start a new application. Okay, using you can inspect the hardware if you like, and you can start the MPLAB IDE environment, so that you can work with the software and the hardware at the same time, concurrently. So any change that you are introducing in the software immediately is taken by the hardware, so you can try for real if it's working or not. One thing at a time. Not this time, because the project is already completed, this phase, you know. A simple up counter of a given number of a stage. But if you like to now modify the thing so that it's counting up and down, after you've got your sketches and you know what to do in the software, you make the modifications, you add the necessary variables or whatever it is, and in the end you try with the hardware at the same time, because there is a modification here as well in the hardware. You have to add the up-down pin and read it, and etc. Right? So this way. So you can do that a lot better if everything is working at the same time, the hardware and the software. So now let's just start the project to compile what is required now. Okay, file, new project, and a standalone project for the microchip P10 F4520 chip, that one. Next, the hardware is not important because we will do that in Proteus, but now yes, you have to select the compiler correctly. This XE8, you say next, and now it's a good time for finding the folder, and you know that the folder is in the right L, CSD, this course, P10, and the counter modulo 1572. So you copy that, you open that location, and now the project is the same, underscore PRJ as usual. So you say, you click the finish now, and it's going to be the time for adding here the source file. Okay, the machine is trying to establish this new workspace. Okay, so you better watch the project navigator, because I don't know, it is not here. So view the project navigator, right? View, yeah, that is the chip, the navigator is down there. So you have the list of different files that can belong to the same project. So now let's add a new existing item, and it's not exactly here but one level above. Or why it has not, we have a problem, you see, something went wrong. You see, you don't have here the correct folder. Something went wrong, so it's a time to, you see, I don't know what has happened, but it is not here correctly written, the folder .x. So this means that we better go backwards to the beginning and start again. That happens many times, you see. You have to pay attention to do it correctly, because now perhaps it's going to work and perhaps not. So it's a good idea to cancel everything, to switch off all the windows, exit that thing, and go back to the folder structure that has been generated now, and let's see what happens, okay? That way. For example, this is CSD, this is the project folder, so let's keep those ones and let's delete anything else, everything else. So now we are starting again. We have the two projects, the two files, one for the hardware and one for the firmware. So let's go and let's start again. You see, there is plenty of time. You better do that correctly in order to avoid complications later. So MPLAB-X is the program environment that you need. So let's repeat. We know that from the previous examples that the machine invents something like a file, a folder that is called .x. So let it be like that. Try and try again if necessary. All right. You see, perhaps you have the start page and perhaps there is a previous project here. So the first thing that you better do is to close all the projects because there is no need for having a previous project opened. So let's close it all, and this is an empty space now for working on it. So the new project. So an embedded project standalone for the P10F4520, like that. So you say next now. Let's click the ICD3 and say next, and now let's click the XE8. You say next. And now let's pick up the right folder, which is exactly the one here listed now. So CSD, this course, P10, this counter. So now let's copy this name. Let's open that thing and let's save that PRJ. You see, the machine generates this project folder, counter mod 1572 underscore PRJ.x. Okay, so that is the right way to do it. You say finish now and let it be that way. Depending on the computer power, sometimes it takes a few seconds and sometimes many more. But in some way, you are generating now this project space. Okay, so let's see if it is working now. The list of possible files, there is nothing yet here, so let's add an existing item. And that one now, yes, you see the first file, that the first folder is the one belonging to the project, and now you know from experience that you have to go one level up, and here is the file. You see, try to do that thing all the time. If it doesn't sound you correctly, if something is left behind, just go and delete it all and start again. That is the way I do it once and again. And in this way, if I have problems, it's because I programmed something wrongly in C, not because of the environment or anything else. And that is a great advantage, okay, naturally. So this is what you've got now, this folder with this file. And now is the time for inspecting that, okay? As usual, let's keep an eye on the software. So the max count, now the reset definitions, and then the same function prototypes, the list of static chart and ints. You see the difference between an int in the current state in the bar queue because we are using 11 bits. So the main program, the same. And now the init system, leave the pragmas as they are, don't touch them. So go straight to the port definition. You see, you can define them all as output by default, And for example, here the bit 3 in this trace A is the count enable active law input that you like to consider. And this is the input. The bit 0 in this trace B is defined as an input because it's the clock, external clock, that is going to move the counter up. And then there is the definition of the configuration bits related to the interrupt. You like to get interruptions from the interrupt external, external interrupt 0. This is what you are enabling here, and the general interrupt, okay? And so you can go and review the state logic that now is a lot shorter because everything goes around current state plus plus, you see? And that goes from one binary code to the next, because if there is a thing that the computer can do very well is to add, because it's in the kernel, you know, it has a data path that is containing some registers to store data like the working register W and many more, and then the arithmetic and logic unit to be able to perform this instruction that very fast. And then you see, once the flag related to the clock interruption is used, you clear it so it can be used again another time. And so the output logic, it's even simpler because this is simply a photocopy. And then the same idea for the TC, the terminal count, and that's all. Right, you see, you read at the beginning, you execute the state logic, you execute the output logic, and finally you write. That's it. And that's the same interrupt vector. And that is reading here, right? And this is writing. This time writing takes longer. Perhaps you have to write 11 bits in different ports. So you have to take it easy and write, for example, here 4 bits and another 4 bits in another port, and this way, right? A part that you see in a very independent way, you will write the terminal count variable. So you see, you can interact with the same port for the reason of writing the TC, and now in a different time later on you can interact again with the same port but for another purpose, writing the code. That is the way it works better, because in this way you have to focus your attention only in one thing at a time. Naturally, everything can be combined and be more efficient, but you know, this is not our problem now. Our problem is to be sure that we understand very well what is this idea of bitwise writing and saving information that is not of interest, so you cannot reset that bits of your not from that are not of your concern. Okay, so let's do that way, one thing at a time, even if it is the same port. It is a good idea to insist on this, right? So this is the code, very well. So now let's go and program the properties of this project related to the compiler, because we like to get from this compiler two very specific things: that it is using the C90 standard, and that generates the COF instead of the ELF. So you apply these conditions, these two parameters, and you click OK right now. And now is your turn to sweep and start again a new compilation, right? And the machine is running. So in not that much time you will get what you want, which is the final, well, some warnings, yes, but that is not important now. You see, related to transitions between signed and unsigned conversions, but that is not important. Perhaps what is necessary now when you get the result is to keep an eye on the memory occupied, and if it is sounding to you, and then you can go and connect this COF to the hardware that you've got in Proteus. So you can just right now, without going to the lab, you can check if everything is all right, okay? So you see, this time I don't know what happens, that it takes that much time to get the final compilation ready. Okay, it's building the project, but I don't know why it takes that much time. It shouldn't be faster. It should be faster that way, you see, but in the end I don't know why it has taken that time. 1 minute and 17 seconds. Well, that depends on the CPU that you have in your portable computer, or in this case in your virtual desktop. Okay, but in the end you've got what you want, which is a program space of 188 positions, you see, or 388 in decimal of the many that you have, and this is only 1.2%. And then what you've got is a data space, an occupation of 14 bytes. You see, that is what you've got. So now you are ready for what? You have to keep this window open, because if you like to make changes here, that is going to be possible anytime you like, okay? You can make any changes later in the same window. Everything is ready now for cleaning and recompiling. For example, if I do that now, you see, perhaps it's faster than before, because, yeah, let's see. It should be faster. Just in a few seconds, yes. You see now, only 6 seconds, and in the previous compilation it was 1 minute, 17 seconds. So it doesn't matter, okay? So let's set aside this window now, and let's open the other one, that is the hardware. So the hardware is looking like this, the same way as your sketch. And you have buttons for setting the clock, you see, by hand or automatically within a clock oscillator, and you have the count enable switch to allow the counter go up and down, and that's all. So you can go to the child sheet and you can associate to this device, you see the properties, for example, 16 megahertz for the clock. And now let's fetch here the right file, and you know that is here in distribution, default, production, and here it is, the one that we have generated just now. Okay, open that thing, connect it to the program file here in this parameter, and say okay. And now you can go to the top. Okay, and now it's your turn to see whether the machine is working or not, because it is that case now. You have the real board on your table in the lab, and you have been downloading the code into the microprocessor computer. So now is your turn to go running this, okay? That way, clicking this button. So the machine has to run. If nothing happens, it's because you see the machine has not the right level in count enable, and now the machine starts counting. You see that fast because you have decided to use a 15 Hz oscillator. That's right, okay? And probably in the last state you will get what you want, which is a green light in the TC 1572. You see the system is counting up at this speed. Is going to take several seconds to reach there. You see, you are using a 30% of the CPU capacity, so sometimes the time that you see here advancing in is not real. It's real in the simulator, but perhaps it's not real time, because executing 1 second of simulation takes a lot of real time. You know what I mean, right? But the important thing is that everything happens for real, animating in this simulation. So for example, now you can stop, you can go step by step, you can set aside your windows, you see. The machine is executing this, you see, instruction by instruction. And perhaps you like to watch now carefully which is the code that you are generating, so you better make room for the current state and the clock flag and the etc 1572 variables. So now you better go to debug and add a watch window and drag these variables here. Okay, and pay attention to the values. You can change the font. For example, let's make this window larger, 16 and bold. Okay, so that time is this way is clearer. You see, you have the variable name and you have the value, and you can see the value in this way or with a different format, an unsigned integer, like a number, okay? No, this one is a binary one, sorry. This is a binary one where you are using only the last bit. The flag is as well another binary variable, and the current state, you better pick, it's an int variable, so instead of signed, you better use an unsigned integer like this, okay? I mean a natural number that has to go up to 1572. So this is the watch window. So now you have the opportunity to see the output LEDs. But if the right output is not yet programmed, no problem. You can still follow what is happening here, watching the variables. And this is the great advantage. You can solve the project first, and then as the last step, you write the outputs, because the internal variables are already here. Okay? So you run that, and you see that the program is advancing as usual, you see. And if you like to stop in the right place, you see, for example, watching the TC value, you stop, and you better go and find this logic associated to the TC. And here, for example, here is a good place to set a breakpoint. So you run now, so you see the machine notice nothing now, but don't worry that when the machine reaches the last state, you see, now stops. So this means that everything worked properly well, okay? And perhaps you see now the variable is still 0 because you are yet to execute this instruction. If now you execute this instruction, you see, you click that instruction, now it goes to 1, and you see, you have not yet written this value. The variable is here, but now because it's a sequence of instructions, remember, you can jump into, you see that you can, with this boot, you can go into the function, and now through these instructions in writing is when you are going to be lighting the LED. Look at this. You can go now one by one. You read the port. You write now the port. So from now on, if everything goes right, this green LED on bottom corner is going to be lighting like this. You see, click. Not yet, because probably it's due to the interactive thing. So when you click that now, it's okay. Okay, it doesn't matter. It sometimes takes a while to go on because that depends on the system of Windows, but in the end you get what you want. And now you can continue working like this. You see? Okay, instruction by instruction, and well, you are stuck here in this, it seems that the system has stuck in this breakpoint, so you take it out and you make the system run continuously now as before. Okay, that way. And now is your turn to make modifications, the ones that you like. For example, it's a good idea to connect here 11 bits so that you can go from any state to any other state. And you can also make this thing reversible, adding a new input. You see, you can add a new input that is labeled this way and is named like this. You see, another button and another resistor and another terminal that is labeled like up and down. So that's just for you to go practicing. This is the way we have to make that circuit grow step by step with several design phases. So in some way, what is given to you is the phase 1, so that you have the things quite organized. Okay, if is what you want is to go through the phase 2. Okay, so that is the tutorial. You see, a lot faster than the previous one. And remember that, for example, in the next unit, in the next project, P11, what we have in mind is simply, for example, to add here in this counter an LCD. So okay, so it's going to be able, the circuit is going to be able to do both counting, representing the count in the LEDs array, and at the same time printing the counter value in an LCD, in a liquid crystal display. That's it. Okay, don't forget, for example, before finishing the demonstration, don't forget to check that everything goes fine. And for example, if you are planning, for example, a 200, let's see if this is right. For example, now if I plan, for example, a 200, that fast, a 200 clock, you see, every 5 milliseconds I will have an interrupt. You see, if I do that, 200 Earth, this means that every 5 milliseconds I will get an interrupt signal. How can I check that, guys? Do you remember? Well, you have to go step by step now, and you have to find the interrupt service routine, because this is what you like to monitor now. If the system is ticking in the right pace, established by the interrupt service routine. So here it is. Okay, if we click breakpoint at this location and you run, you see the machine goes advancing. You see the machine goes advancing, but now you see you have, as you see down there, you see down there, you see you have a 5 millisecond time elapse situation. That means that the counter goes on, as you see in the LEDs and in the variables. The system goes updating states one at a time, but at this pace now, settled by this 200 Hz waveform that you are applying here. Okay, so you can take you can clean this clock flag. You see it works. So now you can clean it. Is possible the same way that you can switch off one by one the breakpoints. Sometimes it is preferable to do that thing of clear all the breakpoints, Control F9. In this way you are sure that now the system is not going to be stopped anywhere. Okay, so now the system is advancing a lot faster, all right, than before. So the full count of 1572 states is here just a lot faster.